So let me get the video started. All right, so last time we talked about structure of the atom, mass number, protons, neutrons, all that kind of stuff. So that's fine, and you'll see some of that on the homework this week and on the quiz on Tuesday. But also, as we move on, we're not going to use these numbers quite as much because realistically, when we're doing chemistry, we're not dealing with individual atoms. So the fact that we have an atom of one isotope versus another isotope isn't going to concern us a whole lot compared to the actual bulk property of the whole thing. So for those of you who have been making some progress, I know I've talked to a couple of you who had questions on some of the homework. You've seen this already, but those numbers on the periodic table, even though I told you last time not to use those for these types of tables, we're actually going to end up using that number more often than these mass numbers on the table. So let's talk about what that is. That number on the periodic table is called the average atomic mass. And what that is an average of the isotopes as we find them based on, or weighted based on their natural abundance. So let's see, where am I at here? Okay, so for instance, let's take a look at silver. Right, silver says number 47. Make a little silver box here on the periodic table. Okay, and the mass number that's given, or the atomic mass that's given there, is 107.8682. All right. So if you're looking at silver in terms of like what we did on Tuesday, what would you guess is the most common isotope of silver? If that number is an average of all the isotopes, what do you think is the most common one? What? Well, that's the atomic number. The most common isotope would be identified by mass number. So maybe 108? Because it's like closest to 108. That's probably what I guess too. But this is why we have to be a little bit careful about this, because it's not. Actually, there is no silver 108. It doesn't exist. The isotopic abundances of silver are, there is silver 107, which is 51.84%. Oops, I don't know why I said 4 and wrote 5. And there's silver 109 at 48.16%. So if you look at the silver in the world, at any given sample of silver, about a little over half of that is silver 107, and a little under half of that is silver 109. There is no silver 108. So where this number comes from on the periodic table, this 107.86 whatever, is a weighted average of those two masses. Now, because we've got so many significant figures to deal with here, we can't just use 107 as the mass of silver 107 and 109 as the mass of silver 109. In fact, those are the mass numbers, but the actual atomic weights are slightly different because of the mass of the proton and the neutron and the electron and stuff like that. So the actual mass of silver 106 or silver 107 is 106.1 0.905 atomic mass units. So like to 3 significant figures, it's 107. But if we need more significant figures, it's actually not quite exactly 107. And for silver 109, the atomic mass is 108.904. And you can look up these atomic masses, but they are not on the periodic table. You have to actually look at a table of isotopes. In general, like when you're solving problems in the homework, those will be given to you, or you'll have to solve for them depending on what the question is asking. Okay, so now we have 2 atomic masses, we have 2 percentages, so we can do a weighted average. A weighted average is, well, you know, like a regular average where you just add everything up and then divide by the number. A weighted average, you multiply each one by what percentage it is to get the overall total. So in this case, we would take, like for silver 107, we would take that mass, 106.905, and multiply it by its abundance, by its percentage, so 0.5184. And then we would add that to all the additional things that we're trying to average together. So for silver 109, that would be 108.904. And its abundance, 0.4816. And if we do that calculation, we should get the average atomic mass. So let's try it and see. So that's 55 point, let's see, we need 4 significant figures, 55.42. All right, so you can see that 107.8682, which to 4 significant figures would be 107.9. Okay. And so that number there is called the average atomic mass, and that's the number that's on the periodic table. It's the average of all, it's the weighted average of all the different isotopes. Another kind of unrelated place that you should be using weighted averages like this is when you calculate your grade. I don't know how they do it in all your classes, but in this class, if you look in the syllabus, the different parts of the class are weighted in different categories. So it's like exams are 30%, labs are 20-something%, whatever it says. So if you want to know your overall grade, you take your average grade in each category, multiply it by the weight, which is that same percentage, add those all together, and then that should be your overall grade. So weighted averages. We're going to do an experiment about mass spectrometry using this in a couple weeks. But for now, we'll just stick with the kind of theory behind it. All right, so let's take a look at what happens when, so that's like the most direct way to do it. You've got your abundances, you've got your masses, you calculate your average atomic mass. What if you don't have that? You might have to do a little bit more creative mathing. Is that a word, mathing? Probably? I don't know. Probably not. Let's try one. So this is the one from the book. I think it's also in your homework. Let's look at bromine. Bromine has 2 naturally occurring isotopes. Bromine 79 and bromine 81. The mass of bromine 81 is 80.9 9163 atomic mass units. And its natural abundance is 49.31%. Calculate the mass and the abundance for bromine 79. All right, so work together on this, or I mean, if you'd rather work by yourself, that's fine, but you can work together on this and try to think about how you would use the technique that we just talked about to figure out what is the atomic mass of bromine 79 and what is its natural abundance. We gotta fill in those two blanks. Good work going on this. Don't worry if you haven't quite finished it up yet. So how do we go about starting a problem like this? What can you get relatively easily? Yeah, so how can we get the abundance of bromine 79? Right, there's only 2 isotopes, so they've got to add up to 100% overall. So if we just subtract 49.31 from 100, we get the abundance of the other one. So what is that? So we do that. 50.69. And if you had multiple isotopes, assuming there were not too many unknowns, you could find them the same way. You could find the abundances because they all have to add up to 100% of however many isotopes there are. All right, so then how do we find that mass of the bromine 79 isotope? What? Yeah, we're going to use the same equation that we used before. So we know that the weighted average of the two has to equal the average mass, which we can find from the periodic table. So the average mass from the periodic table is 79.904. I'm just reading that off from bromine 35. So that has to equal the weighted average of the two isotopes. So that's the one that's given. Times its abundance plus this unknown one that we're trying to solve for times its abundance. All right, so then we can rearrange that equation and solve for bromine 79 and get that its mass is, oops, what'd you get for that one? This will be easier if I just ask somebody. 78.9189. Oh, good. Okay. Yep, looks good to me. All right. So let's talk about how we actually get these abundances. To get these abundances, we're going to use a technique called mass spectrometry. And we're actually going to do this, but I'll show you a picture of it. In a mass spectrometer, you inject a sample somehow. In our case, it comes out of another instrument called a gas chromatograph. But you put in a sample of your substance. A heater vaporizes it, and then an electron beam ionizes the sample. So it turns it into an ion by knocking electrons off of it. Then it gets accelerated through this device, and the heaviest particles are the ones that are least deflected by the magnetic field as it kind of turns the corner. So they're the ones that kind of end up on the outside. So depending on where the particle hits the detector could measure the mass of that particle. And since it's actually giving you a count for every single particle, it's actually counting the different isotopes. So an instrument like this gives you a signal like this. Now this is a very simple one. Let's say you just put pure silver into it. You would have, we talked about the two different isotopes of silver. So you'd have two different peaks for silver, one right about 107, one right about 109. And the height of the peaks, the relative height of the peaks, is proportional to their abundance. So if we looked at one like chlorine, you could take the relative heights of those peaks, and you could actually use those to calculate the relative abundances. So for chlorine, it's about 3 to 1, chlorine 35 to chlorine 37. So if you look at the periodic table, the mass is closer to that 35. It ends up being a weighted average. When we do it in, we're going to do two different ways when we do it for lab. One is we'll just use the instrument to tell us the heights, the abundances, and we'll calculate from there. And the second way is you can actually just do this by hand with a ruler. If you take a mass spectrum, the graph that comes out of this instrument, and you literally just measure the heights of those peaks, you can use that to figure out the natural abundances. Okay, any questions about average atomic mass, calculating those? All right. So while we're talking about the periodic table, let's talk a little bit about how we separate this. And this is perhaps something you've seen before. copy this so we can write on it. Okay. So here's a periodic table with some examples shown on there. We'll talk a little bit later in the semester about where the organization comes from, where the shape comes from. It has to do with the electrons and electronic structure of the atoms. But for now, we kind of want to know more of the bulk properties of it. So one way that we can separate the atoms in the periodic table, or the elements in the periodic table, is metals and nonmetals. So if you can see, I don't know if you can see those colors well up there, but the metals are generally to the left, the nonmetals to the right. The separation is that kind of stair-step zigzag line that you can see highlighted on the periodic table on the wall. And then the atoms bordering that line, with a couple exceptions, are known as the metalloids, which means metal-like. So those are kind of in the middle. They have some properties of metals. They have some properties of nonmetals. All right, so you've probably seen some of these things before. What are some properties of metals? What's special about metals? They conduct electricity, that's one. They're generally good electrical conductors with low resistance to electrical conductivity. What else?
They're malleable.
They're malleable, what does that mean?
Bend them into different shapes and they'll hold that shape.
Yeah, technically malleable has to do with hitting it with a hammer, and like having it spread out, that you can like hammer it into sheets. But yes, like the actual effect of that is just what you said, that you can change the shape of the metal without it breaking. What's the opposite of malleable? Yeah, somebody said brittle, right? Brittle is something where if you try to bend it, it'll just snap. It's like if you take a hammer to somebody's car versus to their window, you're going to get a different effect. Have you ever done that?
No, not yet. No.
Not yet? See how this class goes? Start parking my car somewhere else. Yeah, so the metal will dent and the nonmetals will not. That actually has to do with the electrons too. That in metals, the electrons are delocalized, which means they're not really on the atoms. They're kind of like floating between the atoms. So when you move the atoms around, the electrons can kind of fill in and reorganize themselves, and it works fine. Nonmetals, the electrons are held tightly on a specific atom. And so when you separate the atoms, the electrons come with it, and it makes a break, and that makes it brittle. So that's one thing. The conductivity is another. You can see that the metalloids in the middle are often known as semiconductors because, again, they're not as conductive as metals, but they're not as insulating as nonmetals. They're kind of in the middle. And that's what makes a semiconductor. And so the reason those are so useful in things like computing, transistors, those kinds of things, is you can alter their conductivity. So you can switch their conductivity on or off in different ways, in different directions, and that's what makes them so useful in those types of devices. All right, so we got our metals, our metalloids, our nonmetals. A couple other categories you should know. There are some special names for some of the different groups. So who knows some names of groups of elements? We'll try to fit them all on here. I don't know if we'll all get them there. Anybody know a name? Go ahead. The group 1A? Okay. So yes, group 1A are called, the alkali metals are group 1A. Yep. 2A is alkaline earth metals. Yep, 2A is the alkaline earth metals. Okay, what else?
The one farthest to the right is the noble gases.
Yep, so these over here are called the noble gases. Who knows another one? Go ahead. Mm-hmm. Yeah. So it's actually just these 4 from 7A because the other ones are radioactive and they don't really behave in that way. but those are called the halogens. And does anybody know what this big block in the middle is called? It's kind of like about like that.
Transition metals.
Yeah, the transition metals or transition elements. All right, those are the main ones that you should know. There are some names for the other ones, like 6A are sometimes called the chalcogens, 5A are sometimes called the pnictogens. There's, of course, the lanthanides and the actinides down at the bottom that kind of fit inside the, in between 57 and 72 and 89 and 104. But you should know those names at least: the alkali metals, alkaline earth metals, transition metals, halogens, noble gases. And you should be able to guess whether an element is a metal, non-metal, or a semiconductor based on its position in the periodic table. And you can probably do that. All right. The other thing we can get from the periodic table is that some ions or some elements make ions, and they generally always have the same charge. It may not be 100% of the time because there's always weird exceptions, but in general we can assume that they're the same charge. You should definitely know these, because in the next chapter we're going to talk about naming, and you'll have to know the charges of the ions for that. So here are ones you should know. Group 1A, the alkali metals, will generally be +1 ions. Group 2A, the alkaline earth metals, will generally be +2 ions. Beryllium isn't in that list, Be, because that actually tends to be more of a covalent compound, so it doesn't really make it like a 2+ ion. Then you've got aluminum as a 3+ ion. That's really the only one it makes. Nitrogen, 3-, the oxygen, the 6A, the chalcogens, all 2-, and then the halogens, all 1-. You'll notice hydrogen is kind of written in two different places, and that's because hydrogen can commonly make an ion of +1 or -1. When it makes a +1 ion, it's kind of acting like an alkali metal and making compounds similar to alkali metals. When it's a -1, even though it's still not really a metal, so it doesn't really make ionic bonds in that way. When it's -1, it is more truly ionic, and it acts more like a halogen. It's the properties of halogens. So that's why it's listed in two places there. The other everything else in the periodic table is blank here because we can't predict the charge of those just based on its position in the periodic table. There are some other elements that have predictable charges, and we'll get into that in the next chapter, but we can't just say like, oh, it's in this row, so it's got to be this charge, or this column, so it's got to be this charge. All right. Any questions about that stuff so far? Okay, then let's take a look at the last part of chapter 2, which is about moles and molar mass. Who's heard of this before? Probably most people. Okay. So what we have an issue with chemistry and with molecules in general is we want to manipulate these things that are extremely small. Extremely small. So small that we can't really manipulate them without the aid of extremely fancy equipment. If we really wanted to move one atom around, we would need something very, very fancy. But we don't do that. We take scoops of things in the lab, and we want to weigh stuff out and mix it together. So if you've, we haven't really talked about chemical equations yet, but if you've done stuff with chemical equations in the past, with balancing equations, you know that chemical reactivity is all about counting. It's about one of these reacts with two of these to make three of these, or whatever. Like you have to, or one of these reacts with two of these to make one of these. It's always about counting. That one piece of this reacts with three pieces of this to make whatever. So that poses a problem because we can't count things that are too small for us to count. So what we need to do is we need a relationship between counting, which we can't do, and weighing, which we can do. And that's what the mole allows us to do. So if you're trying to count something extremely small, and you can't count things, and you can't actually manipulate things that small, what do? How can you count very small things?
Usually we don't.
So we're going to weigh them, yep. And so then we need something to tell us like what that means, right? Like converting a weight or a mass to a count. And so the other part of that then is we can count big batches of things. So let's say you've got, I don't know, what's something really small that is good to eat? M&Ms? You can count M&Ms, right? They're not so small that you can't count them, but they're pretty small. But let's say that you wanted a lot of M&Ms. So instead of counting them, you could count bags of them, right? And as long as you knew how many was in a bag, then you could count bags, and that would be a lot easier. You could have fractions of bags, whatever. So the same thing with molecules or atoms. We can't count individual ones, but we can count batches of them. And that batch that we use is called a mole. So 1 mole of something is that many pieces. All right, the most common thing that it's compared to is a dozen. We can write that exact same sentence with a different number. How many are in a dozen? 12. Okay. Functionally, it works the same. I really like donuts. I want lots of donuts. So rather than counting each donut, I'm going to count batches of donuts. 12. Counted by 12s. That does it. I got atoms. They're too small. I can't count them one by one. So I'm going to count moles of them, batches of them, that many of them. Now that number is almost unimaginably large. That 6.02 times 10 to the 23rd. That number is so big that we don't really have a concept of what it means to have that many of something. We just can't, like our brains can't process something that big. So for that reason, sometimes that mole gives us trouble because people think of it as like a special thing or something that only applies to chemistry. But it's really just counting in large batches. It's just a big number, and we're going to say we're going to count these things in these big batches. All right. That number comes from carbon, actually. We define our atomic masses by saying that an atom of carbon-12, so carbon with a mass number of 12, weighs exactly 12 atomic mass units. And so if you figure out, if you then move that to exactly 12 grams, so you convert from atomic mass units to grams, then that is the number of carbon atoms in that batch of 12 grams of carbon. All right. So one thing we can do then is use these numbers to count things, but count them in terms of moles. So a mole is abbreviated MOL. And so we might say that if we have we could say how many carbon atoms are in 2.30 moles of carbon. Okay. So 2.30 moles of carbon, that's like a batch of carbon. 2.3 batches of carbon, 2.3 moles of carbon. But how many individual atoms are in there? Well, to do that, we set it up just like all our other conversion problems from the last chapter. 2.30 moles. And then we're going to convert from moles of carbon to atoms. And anytime you're converting from moles to the number of particles in that mole, whether it's atoms, molecules, electrons, whatever, photons, we'll be using various things like that. There are always going to be that number of atoms or of particles in a mole. All right, so moles cancel there. So I'll end up with 1.39 times 10 to the 24th. Just a note about scientific notation, because we're going to be using these big numbers a lot now. The truly strict standard way to use scientific notation is to always only have one digit to the left of the decimal place. However, in some fields, it is also considered okay to not do that. So depending on how your calculator is set or whatever, you may find it in one or the other. You'll notice that when I multiplied 2.3 times 6.022, I got this number, 13.85. So I could have written 13.9 times 10 to the 23rd. Or I could convert it into the more strict scientific notation, 1.39 times 10 to the 24th. I would consider either of those to be correct. I believe mastering chemistry doesn't care either, but you'll have to check it and see. As long as you've got the right significant figures, I don't think mastering chemistry cares. Okay, there we go. All right, so that's if we want to figure out how many particles are in something, or in a certain number of moles of something. But that still doesn't get us to the point that we were trying to make before, which is how do we actually physically measure that amount of stuff? And to do that, we use something called the molar mass. Which is grams per 1 mole, which can be used as a conversion factor to convert between grams and moles. And the reason that the number was selected the way it was is so that we could use the same numbers on the periodic table that we used for atomic mass units for a single atom and use it in grams for a mole. So the number on the periodic table, I'm out of paper here. Hold on. So if I get my periodic table out here again, and let's look at carbon. So this number that we said was the average atomic mass in AMU is also grams per 1 mole. So for carbon, 1 mole weighs 12.011 grams. And we will likely be using that designation of, or that use for this number much more than we would for atomic mass or for AMUs, because we're rarely talking about a single atom. We're much more often talking about a bulk thing that we're measuring. Okay, so you'll notice I wrote that as a fraction. That's a conversion factor. And we can use that units, the unit grams or the unit moles, and in either orientation depending on the problem that we want at hand. So let's say that we need 2.30 moles of carbon. How much in grams should we measure? Right, so to do that, we're going to set it up just like a conversion, just like before. But this time, instead of converting from moles to particles, because the question's not asking how many individual atoms do we have, the question is asking how many grams should we weigh out. We need to figure out how many grams of carbon there are in a mole. And to do that, we use the number from the periodic table, which is 12.011. So we got 2.3 times 12.011, 27.6, yeah. All right, and that right there is a very, very powerful tool, because now we know, all right, we can go in the lab, we can measure 27.6 grams of carbon, which is easy to do. Get your spatula, get your black carbon powder, just start weighing it out. You get to 27.6 grams, and then we know we have 2.30 moles of carbon. So we've gone from weighing, a thing that we can do easily, to counting, a thing that we can't do so easily. When we get into chapter 4 and we start looking at chemical equations, when we want to count how many of one atom or molecule to use and then figure that out and weighing it, that's exactly what we're going to do. We're going to do these types of conversions. So you should be comfortable after completing the homework in this chapter in doing these types of conversions, converting between grams, moles, and number of particles. There's nothing new about it except the numbers. The technique is the same as the typical, metric unit conversions or whatever that we did in the last chapter. Okay, let's do like a kind of a weird problem. There's some in the homework that look a little bit like this. And we'll talk about how to talk through it, how to think through it, how to form a strategy to solve a problem like this. So this is an example from the book. An aluminum sphere contains 8.55 times 10 to the 22nd atoms. The density of aluminum is 2.70 grams per cubic centimeter. What is the sphere's radius in centimeters? Give me a second to get that down. So this is a molar mass mole type question, even though the word mole doesn't come up anywhere in that question. How do we know that we have to use these concepts of moles to determine or to get the answer? What? Yeah, so that's a good sign. Anybody else? You want to add to that? What were you thinking on that one?
Well, I was going to say that you're
Yeah. So that's precisely the thing, that we've got these large numbers, and specifically we have to move from a count of something to a mass of something. If we're talking about a volume of a sphere, and we're talking about a mass, like a density, we've got mass there. And then we're also given something about a count of atoms. So we can think of this as a conversion where we want to start with the number of atoms. And we ultimately want to convert that into grams. Once we have grams, then we can get volume, and then we can get radius. We'll have to look up the equation for a sphere. I don't know if you guys remember that, but I don't. Luckily, it's here. But once we have grams, then we can use the density to get volume. Because that's what the density gives us. So we can get volume from grams using the density. How do we get from number of atoms to grams? Number of atoms is counting, grams is a mass. So how can we relate the number of things to how much they weigh? Yeah, with moles, right. Exactly what we've just been doing. So from the number of atoms, we can figure out how many moles that is. And then from the number of moles that is, we can use the molar mass of aluminum to get the grams. All right. So now that we have a little bit of a plan, see if you can work through this either on your own or with your group or with a partner. I will also tell you that the equation for the volume of a sphere is that the volume is 4/3 times pi times the radius cubed. You do not need to memorize that equation for this class. All right, did you get this thing to convert? Maybe? Getting there? All right, let's try to follow it through. Let me show you how I would do it. Again, if you think through this in a little bit different way, that's okay. We can come to the same conclusion from different paths. I like to always follow the units. If I can kind of turn anything into like a simple linear conversion problem, like I'm going from this to this to this to this to this, that's going to just make things easier for me and less likely to make errors on units. So I set up my little path there. So that means I'm going to go from the number of atoms to moles using my big number, then moles to grams using a molar mass, then grams to cubic centimeters using a density, and then I can solve for the radius using the volume equation. So let's see how that works here. All right, so we're going to go from atoms to moles. Oops, already messing up here. And then moles to grams, just following my arrows up there. It's out of the way here. And then grams to volume. All right, so I can cancel atoms, cancel moles, cancel grams, and end up with a volume. Now I can fill in my numbers, and since I've got my units set up properly, I'm less likely to make mistakes than like putting the numbers on the top or the bottom in the wrong spot. So I know if I look at how many atoms are in a mole, that there are 6.022 times 10 to the 23rd atoms per mole. Then if I'm looking at aluminum, I can look at grams per mole from the periodic table. So that's 26.98 grams per 1 mole. And then finally the density, which is given in the equation, 2.70 grams per cubic centimeter. All right, I got to be a little bit careful about my scientific notation calculations here because I don't have a scientific calculator, but we can figure that out. So 8.55 divided by 6.022 is going to be 1.42, let's say. I'm dividing 10 to the 22nd by 10 to the 23rd. So that means I need to then divide this by 10 also, because there's 10 difference between those two. If you have a scientific calculator or a graphing calculator, you don't have to worry about that because you can just type it in as it is. Times 26.98 divided by 2.7. I should get about 1.42. Is that right? Is that what you got? Okay. Okay, so that's a volume. We're not quite done, but we've done the basic conversion part. The rest is just that we have to find the radius. So we take that volume and we plug that into the volume equation and solve for the radius. Which you should get something like 0.697 centimeters. Is that what you got? All right, great. Just to review, to do that, if you don't see that immediately, you would multiply both sides by 3/4, divide 1.42 by pi, and then take the cube root to get the radius. All right. Questions about that? So that problem is, there are several like it or there are some like it in the homework. But the idea is anytime you're going between counting something and weighing something, you're going to need to use moles. The rest of it is more like Chapter 1 type standard unit conversions. But when we go between the counting and the weighing, that's when we need to use moles. All right. Let's try another one. Okay, so there's a couple ways to do this problem. We're going to talk about a couple different strategies. Which contains the most atoms? You've got some masses of some different elements. So this might make like a nice multiple choice question in a quiz or exam. How would you do a question like this? What's like a plan?
Well, I want to figure out how many atoms are each mole, because each atom is a different size and it can contain more.
Okay, so that would be one way to do it, is to do a calculation for each of those, right? You'd say convert grams to moles and then moles to atoms, as we've done. You have another strategy?
I would just convert grams to moles, and whichever is more higher of a mole, that's more atoms.
Yeah, so that saves you a step, right? We could always go calculate atoms, but getting to that last atom step is always going to mean multiplying by 6.02 times 10 to the 23rd. So if we're multiplying everything by the same factor, we don't really have to do that. A number of moles is good enough. But there's even an easier way to do it than those. Those are fine. Those are great ways to do it, and you know, that'll definitely get you the right answer. Anybody think of even a quicker shortcut?
Use Google.
Okay, well, so hopefully not in a quiz, but yeah, for homework, maybe. Does anybody have good ways of like secretly using Google on exams?
Is the middle one the most?
The middle one is the most. How did you figure that out?
I don't know.
Okay, so that's a quick way to do it. Just guess and hope you're right. Yep.
Well, no, I think that's right. I feel like the atomic mass has something to do with it, right?
Yeah, so we can look at these three on the periodic table, and we can say, oh, wait a second. Okay, titanium has the lowest mass, or we can notice that each of these quantities is sort of close to the atomic mass on the periodic table. So the titanium, you've got just under its atomic mass. So actually, no, you're not right. I don't think it's the middle one. I wasn't looking at the numbers. Titanium, you can see that its atomic mass is about 48, and we've got about 45. So you've got just under a mole of titanium. For chromium, it's about 52, and we've got about 55. So we've got just over a mole of chromium. And zinc is 65, and we've got 60, so we've got under a mole. So the only one that's over a mole is the chromium. And so that one must contain the most atoms, because that one's the only one that's more than a mole. So we can figure that out without doing the calculations. So this one's greater than 1 mole, and these are both less than 1 mole. And that's really all we need to know for that, to answer that question. Now, if they were all a little more than a mole or all less than a mole, it's probably worth doing the calculation, because that might be hard to figure out. Or if it said rank them, 1, 2, 3, we'd have to at least calculate those last two to figure out which one is more than the other. Okay, questions about that? All right. I think that's. Oh, we're in a little early today. So I don't want to go into the next chapter right now. We'll start that next week. But we got about 10 minutes left up here before we go downstairs and work on the group problems. Are there any problems that have come up for you during Mastering Chemistry that you want to take a look at for Chapter 2 so far? If you want to take a look at the stuff you've been working on, if you've got any questions, this is a good time to ask them. While you're doing that, I'll tell you about my best Chem 121 cheating story, since we were talking about looking stuff up on Google and whatever. I was giving an exam one time, and a couple people in class knew each other, apparently. And one of them was writing on their scrap paper, like, what is 15, question mark, and then holding it up to the other student, and then the other student would like write down an answer and hold it, like literally like hold up the paper like in the air, and I was right here and I was just staring at them, and they did it a couple times, and so I went over and was like, okay, that's cheating, and they denied it. They're like, no, we didn't do anything. Like, you're holding up signs. Like, you're holding up signs. I see, like, it's right there. Nope, we didn't do anything. We just continued to deny it the whole time. So, that was, like, I just felt like I was in, like, a dream or something. Like, I have your sign. It's right here. It's like, it says that on there. And they're like, no, I didn't write that. Okay, I don't know what to do with that. So that was like the most ridiculous cheating story I've ever seen. Yeah.
For one of my professors, some kid taped the notes in front of the podium.
Tape like.
In front of the podium. Where it says
oh, right here.
Yeah.
That's pretty good. That's a pretty good one too. All right, so Mastering Chemistry questions, problems. Anybody having issues with any of them yet? No? They're all going well? All right, so just some reminders. We can, I don't know if we can start early downstairs because I think there's another class, but we can just take a little time. So Tuesday will be a quiz on Chapter 2. All quizzes in this class should be considered cumulative, even though they might not always actually be cumulative, but just because stuff is always related to other stuff. So just because it's a Chapter 2 quiz, like the problem that we just did with the sphere, you still need to know density, you still need to be able to convert metric units and things like that. So assume that stuff is still going to come up on the quiz on Tuesday. The Mastering Chemistry is Chapter 2 to Monday night. I'll have to check the deadline on that, but it's certainly coming up. Then we'll have Chapter 3. I believe Chapter 3 is the last chapter before the first exam. So we'll be working on Chapter 3 next week. As with everything else, it works much better if you work ahead a little bit before you come in here. So you can watch old videos of class online, you can read the book, you can find other books, you can find other videos of those concepts. Chapter 3 is a pretty standard chapter in general chemistry, looking at naming compounds and writing chemical equations, balancing chemical equations, and types of chemical equations. So you shouldn't have any trouble finding that kind of information. You got an extra day this weekend. If you can spend a little time working ahead into that chapter, it'll really help you out and when we actually start going through it together next week. All right, sounds good? Okay, let me know if you have any questions, or otherwise I'll see you downstairs at 9:30.